G'day guys, how's it going? So in this video, we're going to talk about memory in, well, Rust and most programming languages, but specifically for this video, Rust, okay? So firstly, the two types of memory that we talk about when we're talking about applications is stack memory and memory that goes on the heap, right? So a stack is pretty organized, it's ordered in a particular way, therefore it's pretty easy to get things in a fast manner, right? A heap, a little bit more unpredictable, but is designed for other particular situations that the stack can't deal with. And we'll get to those things a little bit later, okay? But for this video, we're just going to focus on stack memory. So, what is stack memory? Well, essentially, if we think of a pile of plates in your cupboard and how you would put them away and how you would grab a clean one, right? You would think of the fact that you would put the first plate down. This is putting them away, that is. You put the first plate down, then you put the next one on as you clean them and put them away, right? And then at some point in the future, you need to get one to prepare a meal, right? On that situation, you're going to grab from the top, right? Because it's easy to grab from the top and not have to worry about potentially breaking anything above it if you were to pick from the bottom, right? So that's usually how people deal with plates. You stack from the bottom, you move all the way to the top, and then when you need them, you grab from the top until you reach the very bottom. Cool. Stack memory operates in a similar fashion. And we call this approach a last in, first out manner behavior. So when we mention stack memory, though, we talk about the concept of pushing things onto a stack. So that is the idea of putting things from the bottom and putting one on top of each other, right? We push onto it. It's a pushing manner to which the most recent thing is pushed to the top of the stack. And then we grab something else, we push to the top of the stack. It's always on the top, right? And when we end a particular thing, which we'll talk about in a minute what that is, we take it off the top. And then we take it off the top. And then we take it off the top. And by doing it in this manner, we're actually increasing the performance. Now, where stack memory usually sits, for those who might be interested, it's usually a combination of the CPU's cache as well as an organized region of RAM. Okay. And that's all kind of worked out before the application starts based on the fact that at compilation time, you can determine what that size of the stack memory is going to be. Right. So obviously, being organized, it's going to be fast as opposed to a heap, which is a little bit more disorganized and a little bit more random. Therefore, it takes more time to create entries and fetch entries. Cool. So, what kind of stuff goes into a stack, right, in Rust? Well, the first thing that we talk about when we talk about stack memory is dealing with function calls, or what we call either stack frames, or some people also call it the call stack, right? So basically, it's all the calls that we make to functions inside of Rust are kept inside the stack, and this is done on a per thread situation. So we haven't talked about threads just yet, but in a multi threaded application, each thread has its own version of a stack, and therefore any function calls that it maintains. We'll worry about that a little bit later when we get to threading. But just keep in mind, just to be politically correct, that's how it works, right? So the first thing we store is function calls in as stack memory. But associated to those function calls are going to be local variables, right? So we'll see a function that has a let, and we store like a number, something like that, right? Well, what gets stored in the stack along with those calls or the stack frames is any data types that have a fixed size. So think of your integers where you can predict the number of bytes it's going to be at compile time. Think of your floats, which also can be determined at compile time, like i.e. it's either 32 or 64 bit, and usually defined so. Booleans have a size that's fixed. Chars, even though it's a Unicode character, that also has a fixed size. And even to some respect, what we've seen so far, some arrays and tuples. Now, I won't say completely that arrays and tuples go into the stack, because there are edge cases where they don't. But I just for now, it's potentially possible that an array and a tuple can go into a stack. And we'll kind of cover where that fits later on when we talk about the heap. All right, but for now, just think that most fixed size data types that we've seen so far will go into the stack along with the function call that it's a local variable to, right? Now, there are some situations where that may not be true, even for these data types. So one of them could be if a variable, for whatever reason, needs to be shared between multiple threads, i.e. you're doing asynchronous programming. Again, we'll talk about that a little bit later. Or if we're sharing a variable across multiple function calls. And that's different to passing in variables as arguments. We're talking about if we're using some global value and it's being used in multiple calls. That's not going to be stored on the stack. That's going to be stored on what we call the heap. Okay. So now that we have a slight idea of what the stack is going to be used for, let's actually see how it could be used in real time with an application that's executing, right? So just make sure, just to make the distinction, most of what gets stored on the stack or being allocated on the stack will be determined at compile time. However, the actual execution, what goes on the stack at what time, is based on an application running in real time, okay? So let's look at this program that we have. Basically, it does 3 calculations on line 23, 24, and 25, right? And then it prints the results. Cool. So obviously we're going to start at main when we execute this program, and then it's going to detect that we have some variables and we have those 3 calculate functions, right? So when it does this, it goes, okay, we see that we need to execute the main function. So the first thing it's going to do is say, okay, let's put something on the stack. So our first stack frame or stack call or function call is main, right? So it has 3 local variables of A, B, and C, right, of 1, 2, and 3. And then it has 3 more local variables, which are the result of calls to calculate, right? So those can't be determined immediately. We have to actually call those functions. So then the next step is we eventually hit the first calculate call, and that's line 23. We go, cool, we need to call calculate. We're going to pass in A, B, and plus. So that's 1, 2, and plus. That's going to lead to us coming up to our calculate function, going, okay, that's going to map to X, Y, and op. So when that happens, we're now going to push a new entry onto the stack on top of main. So that's the other thing we mentioned before with the plates. This is now putting that plate on top of the previous plate. So calculate will be pushed onto the stack at this point. And then you can see X is 1, Y is 2, and op is plus, right? And this R is an inferred variable, which is the result of that if expression on line 11, or the if else between line 11 and line 15. Cool. So then we look at the code, we go, cool. We're going to get into another function call called add because the operator was a plus symbol. And at that point, we now come up to add and we go, okay, we're now going to have X and Y also be equal to 1 and 2. And so we define that on the stack, just like so. And we still don't know what R is yet because we haven't executed the expression on line 7. So then we do that. We execute the expression on line 7. That gives us a result of 3. And then we continue on to the end of the function, right? Now, once we hit the end of the function, and basically we no longer need anything remaining in this function call, this function call will now be popped off the stack, like so. And it's gone, right? So now we come back to calculate. Now, when add was destroyed, it actually assigned the value of 3 to R, which in this case is the result of that add function, right? So we know what R is. We continue through. We hit its end of function call. At this point, then R1 will become 3 in main, and then calculate will be terminated. Then we move to line 24, and the process repeats itself, right? We call calculate. We know the parameters. We set them as variables in the stack. We then know we're going to hit add. We finally get to add. We push that onto the stack. That's 2 and 3. We get X plus Y, which is 5 as R. that gets returned to calculate, and then basically add is removed, calculate ends, it assigns 5 to R2, and then the process repeats for R3, which is going to do a subtract. So you see subtract go onto the stack, and hopefully by now you're starting to understand what's going on, right? R is now 1 because 3 minus 2 is 1. Then we assign 1 to calculate, and then basically subtract is destroyed and popped off the stack. Then calculates destroyed and popped off the stack. And then essentially we get back to main. We finally hit the end of main, and that is also popped off the stack and destroyed. And that is the end of our application's execution. Cool. So that's obviously a very simple example, but it does demonstrate how we push things onto the stack. We evaluate the variables that are associated to each function on the stack, and how we remove them from the stack. Now, the other thing to keep in mind is when we pop things off the stack, all the memory that was associated to those local variables are cleaned up, right? And we'll talk about this a little bit more in a future video, but they're cleaned up and essentially it's given back to the operating system. Cool. So that's it. That's what I'm going to have for this video for now. So hopefully that helped you understand stacks a little bit better, or stack memory, I should say. But I'm going to go now. So thank you for watching, and I'll see you all next time.